Okay, hello everyone. I'm Gary from the Programming Language and Machine Learning Lab of 강원 National University. Today, I will present a review about the paper entitled with UniXcoder. UniXcoder is pre-trained model, unified cross-modal pre-training model for code representation. The main goal of this research is code representation. If you are going to talk about downstream tasks, you should have to have good code representation model. So this research paper is all about these issues. Authors are from these three institutions. So this paper is published in 2022 in Association of Computational and Linguistic. So my presentation outline looks like this. First, I will introduce you about this model, UniXcoder, and contribution of this research work. Then we will see the related works. Actually, this related work section have a lot of existing models which are used for compare and contrast with the proposed model on the later presentation slides. This third section will see the UniXcoder is actual input representation, model architecture, pre-training tasks. Then we'll see the experiments and results in the fourth section. Finally, I will conclude the presentation. So when you talk about the UniXcoder, it's pre-trained model. Actually, this model is built on top of the model so-called UniLM, Unified Language Model, retraining for natural language understanding generation. It's written by Dong et al. It is published by 2019. Maybe some people have some familiarity with this model. So this paper is built on top of that architecture. So this provides both auto-encoding and auto-regressive tasks. It uses cross-modal contents. When you say cross-modal, text source codes, source code commands, and the AST representation of the source code. And they have create one-to-one mapping function for converting AST to sequences. So the contribution of this paper is they propose this unified cross-modal pre-trained model, which leverages multimodal contents. They have also contributed one-to-one mapping function, which is very effective mapping function. So utilizing this code commands, and you will see later on the presentation, they have also used contrastive learning to represent semantic embeddings of source code. And so they introduce one source code task, which is called zero-shot code-to-code search. We take query of source code, then we find functionality similar source code with another language or with the same language. So significantly, this model have outperformed almost most of the downstream tasks. When you see the related models, which is three groups of source code models, encoder only, which contains covert, codebert, graph codebert, and sync covert. And also the decoder only models, which have GPT-like models, GPT-C, code GPT. And also we do have also encoder decoder models. Basically, they can be represented by PLBERT 45. Also on the later publications, 45 plus also. Most of you have been familiarized. So the special issue in this paper is this model uses all of the source code structural information from the AST using the mapping function. We'll see what is mapping function and other details in the later slides. So here is an example for code search. Just as we know in code search, we take natural language texts or written texts, then we retrieve source code, which have matching functionality with our texts. So in this example, just these authors are comparing the effectiveness of UniXcoder with respect to other existing models. So this function is Python dictionary ranking function. We are retrieving Python code with this query. So most of the models are not retrieving the correct source code which matches our natural language text query. So here is, if we run this source code from our code editor, it can give us a good result. So when you see the input representation of this UniXcoder model, we'll begin by this AST tree. We use any AST parser, but these authors used 3-seater AST parser package. So we begin our module, then we enter the function definition. Under function definition, if you see this function, actually this function is simple function which defines about mean function. So we enter to the entire attributes of this source code. Here we do have the diff keyword and the mean function. Under the mean function, we do have parameters. Should have to split them in such a way. Here are the actual parameter data and the opening and closing brackets. This is just the semicolon, which is language specific, in the case of Python language. When we enter to the definition or to the definition body of the function, they represent it by block. Under this block, we do have expression statements and return statements. So under expression statements, we do have assignment statements. Then we take the variable n, the assignment operator. Here also we do have a len method. So they assigned it this node by call. They call the len. Then the argument list, actual arguments, which is having data. Then the actual source code tokens will be represented in such a way. The same process will go to the return statement. So if we see in this AST tree, every of the source code, including the language specific symbols, are already available here. Whenever we talk about functions, keywords, operators, methods, variables, and so on. So the mapping function is, it is converting this all attributes or all nodes and leaves of this AST tree to sequence tuples. We'll see the mapping function here. Its input is AST tree. The tree node, it may be leaf node or actual root, but is initialized by the root. Then the final output of this conversion is flattened token sequence. So here is our function. It takes the root, and we initialize the sequence, empty list sequence. Then we take the name of the root. If the root is not actual root, or if it is leaf, we append the name of the leaf to the sequence lists. Else, we consider that this is a node, or we do have subtree. So we enter to the entire subtree in this way. We take the name of the node suffixed by left. When we enter to the subtree, which means we are traversing to all the children of the subtree. Here, we iterate through all children of the root, or through all children of the particular subtree. Then we call recursively the function f throughout all child. So finally, when we finish our traversing, we finish by taking the root name, or the root node's name, followed by the right suffix. So in all over this process, we can understand that root name is assigned by suffixing right and left. On the beginning, we assign by suffixing with left word, and the end of our traversing throughout the subtree, we end by suffixing with right. Here is an example subtree with parameters on the previous slide. We see here, we take this parameter subtree. We have this parameters node and this actual source code tokens. Then we take the parameters name. Then we add the word left. Then the actual leaves, or actual source code. When we finish traversing this subtree, we add the name of the node followed by right. In this way, all of the subtrees will be traversed in such a way. Then we convert the sequence in this way. If you have any question to this point, you are welcome. Okay, I will continue. So in overall this modules process, we do have a source code assigned by C, some particular source code. The source code may have comments, and we do have flattened AST token sequences we have converted in this way. Then the input of this module is concatenation of these two sequences, sequence of comments plus sequence of the flattened AST tokens. Here is the model architecture. On the first block, we do have stacks of transformer layers. We take this inputs prefix plus comment plus flatten AST. Prefix is nothing but is indicator of whether the UniXcoder is operated in encoder only, or decoder only, or encoder decoder. So we pass throughout all these processes: token embedding, positional embedding. Then we pass through all the layers. Then we yield the hidden representation of the source code. So on the second block of this module, we do have this attention mask mechanisms. The encoder only, we use bidirectional. So every token can attend all other tokens and itself. The decoder only, we attend only previous tokens. That's why we have blanken these feature tokens. On the encoder-decoder model, we attend all tokens from the encoder side plus tokens previous to the current token. So this is the some illustration about the attention mechanism in this model. The third block is about pre-training tasks. We do have masked language modeling. The second one is unidirectional language modeling, or we can say autoregressive modeling. On the third one, we do have demising objective. These are the main pillar training objects of this model. But the UniXcoder have also two additional pre-training tasks. One is, which is leveraging contrastive learning. Second one is cross-modal generation. We'll see on the further slides. If you do have any question to this point, you can ask me. Okay, when we say about the model, there are some assumptions. We do have n numbers of transformers. We do have hidden states of all the representations in this way. So in the previous, if you see this prefix, these are the prefixes. Enc means UniXcoder is working as encoder model. DEC means is decoder. So if you use E2D, UniXcoder is operating as encoder-decoder model. These are the computations for Q, K, and V, all the available matrices, which are we are already familiarized in the transformation network. So we compute them using the previous hidden state output, HL-1. The attention head in this model is computed in this way. The original paper of transformers network, we didn't have this one. Here we add M here, then we multiply these all terms by V. These are all about the model. We'll see the pre-training tasks. The masked language model, MLM, is the same with BERT masked language modeling approach. It takes 15% of the tokens from the input for masking. 80% of them just replace with mask symbol. 10% of them just replace with random tokens. And 10% are left unchanged. It's the same to the BERT approach. We compute the objective function using the MLM loss function. In the case of unidirectional language modeling, it supports autoregressive tasks. So pre-training is encoder only. So it's predicting of the next token conditioned on the previous tokens actually. So the loss function is computed in this way. We compute negative log of the xi conditioned on the previous tokens of this sequence. In the case of demising objective, we use also here, we use masking, but the masking is randomly. So in this pre-training objective, input sequence are split into chunks first. Chunks means splits of the source code sequences. So the authors use this method to split those sequences. N is the length of the input. R is corruption rate. They use 15% in this paper. L is just is the average length of the masked spans. Then the next process in this objective is randomly masking each of the chunks. We split these tokens into a number of chunks. Then we mask randomly. Then the output will be the masked spans, which are represented as y0 through yn minus 1. All of these masked spans are preceded by this symbol, mask k. So the loss function, the objective function will be computed by taking this masked spans plus the previous sequence which are shown here. The next one is how the UniXcoder is working with semantic understanding of the source codes. For semantic embedding, they use two pre-trained tasks. First one is multi-modal contrastive learning, MCL. The second one is cross-modal generation. The first one is contrastive learning, which uses dropout variation for creating augmented inputs. Actually, the dropout technique is done on the hidden representation of the source code. So the second one is cross-modal generation. It's nothing but is consider it as generation of comments from source code. You'll see in the later slide. So in the case of multimodal contrastive learning, they take the same input of same batch, then they give different dropout values for the same inputs. So in this case, those representations which do have the same or close distance with the original hidden representations, they are considered as positive examples, whereas the remaining representations are considered as negative examples. So the objective function or the loss function will be computed using a contrastive loss in this way. The second one, cross-modal generation, is first the model is required to generate comments from the actual source code input. Then those comments will be used for two purposes. First, they use it to understand semantics of the source code, because the comments are already taken from the same source code. Then the comments are language independent because they are natural language texts. So they can use it to align representations across different programming languages. So the objective function can be computed in this way. Loss function can be computed by the negative log of given the generated comments conditioned on the flattened tokens and the previous comment lines. Here is the architectural demonstration of this semantic representation. Parsing and mapping is the same to that we have seen on the previous slides. We take the source code, we generate comments, then the UniXcoder leverages this source code based generated comments for its semantic understanding on its hidden representation. Then in the case of hidden representation, we filter out the final outputs using mean pooling computation. So as I have told you on the previous slide, the the variants or the representations which are having close distance with the original hidden representation will be considered as positive, whereas the remaining representation will be considered as negative. So in this way, the model will be trained to take the semantic meaning of the source code. So for semantic embedding of the comments or natural language texts, they use some sort of technique. One technique is they exchange the source and target inputs at 50% probability, which means they exchange 50% of outputs as input, 50% of inputs as output. The second technique they use it for determining or for solving the gap between fine-tuning and pre-training. They use to drop some non-terminal symbols in AST at 50% probability during pre-training phase. In the fine-tuning phase, they use only the actual source code or leaves, or we can say terminal. Actually, for clarity, if we go back to the mapping function, if you see here, the parameters left, parameters right, these all are just non-terminal AST representations. The actual source code tokens are this one. So they are providing some reasons. They state that on their paper, if they use all the non-terminal sequence in their training, the pre-training computational cost will be high. So for that purpose, they remove 50% of those tokens in the pre-training stage. So in the fine-tuning, they use only the leaves, which means actual source code. If you see the experiment, it's actually the same architecture with the unified language model pre-training for natural language generation and understanding, which is published in 2019. But they do have their own hyperparameters. They use 12 layers of transformer, 768 dimensional hidden states, 12 attention heads. They use 50,000 subordinates of byte pair encoding. They also add 1,416 additional special tokens. This is for non-terminal symbols of the AST, flattened AST. They use this amount of functions paired with commands for multimodal purpose, actually, for multimodal data. They referred as it takes 8 days for pre-training this model. They use this equation for sampling for every programming language in this training. Actually, these 6 programming languages do not have the same proportion of data set provision. So in order to penalize the programming language with high data source, they use this formula. The alpha is constant 0.7. This is just it is the ratio of number of samples with particular programming language to the total programming language source tokens. So they use this computational form to sample their input. When you see the downstream tasks, we'd have such numbers of downstream tasks. You see here, let's say clone detection, it uses two datasets, POG104 and big clone bench dataset. POG104 is a dataset containing 104 problems, which are written in C and C++, containing 500 programming problems. So these are just split based on the problem domain. We do have 104 problem domains. They split in this way: 64, 16, 24, as train, evaluation, validation, and test sets. The big clone bench datasets have also this data split setting. In the code search, they use three datasets: code's dataset, which do have 10,604 search logs of Microsoft Bing search engine. These all data have annotated by human annotators. The second dataset is CSN. It is created from the code searchlet by removing some unnecessary details or some source of attributes. ADV-test is subset of this dataset. They take the Python language only from this dataset. So we can refer on the later slides. We do have table 6. Code summarization is they use the codex glue team dataset. We can refer from the later slides. Code generation, they use a concode dataset, which have 33,000 Java projects on GitHub. They don't have this dataset split setting, 100,000, 1,000, 1,000 for training, validation, test splits. They use Pi 150 and GitHub Java corpus for code compilation downstream tasks. This Pi 150 is just Python source files dataset, which contains 150,000 from GitHub. This is also containing 14,000 Java projects of the code compilation data are just in this way. The next one is zero shot code-to-code search. They take the split of different programming languages. They take Ruby, Python, Java. These are the data set composition of these three programming languages. Because the code search takes one programming source code, then we are required to search the source code with the same functionality, either from the same programming language or from other programming languages. Here are the data statistics. This is for CSN data is for code search. The later one is for code summarization, which is taken from codex glue. Here are the experimental results. We see here, we see in the case of code understanding, we do have clone detection and code search. So in most of the results, UniXcoder is dominant. Most of the results except this recall matrix. All of the results are outperforming the existing models. The next one is a code summarization and generation, which are generation tasks. In this case, a little bit, the UniXcoder is a little bit outperformed by codex code T5 base. The authors have provided their own reason for this result. First, they discussed that code T5 base have big size in case of model. The model of T5 base is bigger than UniXcoder. The second reason they have provided is they have collected more data in the T5 base. Actually, they put in stats in number 50% more data have provided to T5 base, which is not public commercial data set. So for this reason, the UniXcoder performance is downgraded here. So in this case, if you see the AST is better than the UniXcoder with AST. So AST do not have some effectiveness in the case of the performance in generation tasks only. This is some results about the code summarization per every programming language which are considered in this setting. Here, as we have seen on the previous slide, T5 is just outperforming UniXcoder. The reason is what I have discussed on the previous slide. Next one is code completion. In code completion, UniXcoder is outperforming all the existing source code models, especially in the accuracy of Java corpus dataset. They have achieved 2.3% of efficiency than the all other existing models. The next result we should have to see in this model result is about zero-shot code-to-code search tasks. We take Ruby source code, then the models are required to search source code in Ruby, in Python, in Java. Same to that, we take source code in Python, then we are retrieving Ruby, Python, or Java source codes with the same functionality of our query. The same to that, we take query of Java programming language source code, then we are required to retrieve the same functionality source code written in Ruby or Python and Java. So this in this setting, UniXcoder is outperforming all the existing source code models with extreme margin. When we see the ablation studies, the block of results under the UniXcoder are ablation studies without contrastive learning, without cross-modal generation, without comment, without AST, using BFS traversing algorithm, using BFS traversing algorithm. So here we can see that the contrastive learning, cross-modal generation, as well as commands and the AST flattened sequence of this model approach have good contribution for the effectiveness of UniXcoder. And also, as I have told you, they use the tree traversing mapping function F. So they say that this tree traversing model algorithms are already, most of you are familiar with this breadth first search and deep first search algorithms. These all are just less in performance with the mapping function which is used in UniXcoder. In the case of generation tasks, everything is okay. But in the case of AST, the AST do not have any effectiveness on the generation tasks, as I have told you on the previous slide. In the case of AST, better result is achieved when we use the model without AST. That's why we have low results in the UniXcoder here. You see this result and this result, they do have different outcomes. So in the case of code completion, the contrastive learning, cross-modal generation, comments, ASTs all contribute to the better performance of the UniXcoder. The mapping functions, the mapping function F, which is used in this UniXcoder, is better than this two tree traversing algorithms. So the same is going to the zero-shot setting code-to-code search. The UniXcoder in this setting is outperforming all the existing models. In the case of ablation study also, whenever we use contrast learning, cross-modal generation, when we leverage comments and ASTs, we do have good result, especially it is very extremely high result in comparison to the existing models, as well as in comparing with the ablation study results. For example, if you see here, without contrastive learning, there is a gap. We have 5 difference. A lot of difference is achieved without the contrastive learning and with contrastive learning. Same that with the cross-modal generation and without cross-modal generation. So when we summarize through all the ablation studies, this research work, both contrastive learning and cross-modal generation brings effective for the UniXcoder. Comments improve both code understanding and generation. Though AST is boosting code understanding, but it doesn't improve the code generation tasks. So if we talk about the mapping function, the mapping function is effective than this two tree traversing algorithms. So when you conclude the presentation, UniXcoder is a unified cross-modal pre-trained model designed for code representation. It has also shown as good effectiveness on most of the source code tasks. When we say a cross-modal, it takes source code, AST, and natural language texts or commands. So in this work, mapping function is effective, and the authors used this mapping function to retain all the available structural information from the source code. It's also better than BFS and DFS tree traversing algorithms. So, two new pre-trained tasks, MCL and CMG, are also good for semantic understanding. In general, UniXcoder outperforms previous pre-trained models in almost most of the source code tasks. I have finished my presentation. If you have any question, you can ask me. Thank you.
네, 감사합니다. 질문해 주시면 좋을 것 같습니다. So Gary, I have a question, quick question. So why do they choose the pre-order traversal function as the transformation method for transforming a tree into sequence, not the other traversal orders like in order or post order traversals?
I think you are asking me this mapping function, yeah, Professor?
Yes.
They have first, this mapping function takes all information available from the source code, which can be used for their input representation purpose.
Yes.
If you see here, nothing will be left from the available source codes tokens. The mapping function is one-to-one function, by the way. They have also proved the function's one-to-one property in the appendix of the paper. For more details, everyone can refer there. So one-to-one function is there is some sorts of nodes and subtrees lives in this AST tree. So every attribute in this tree is mapped to any AST sequence or any sequence token from the if you see in this case parameters, it have taken all the available information in this tree. Nothing will be left unrecorded from this tree to the sequence token representation. That's why they prefer. And also they have make ablation study between existing you see here.
Yes.
If you see here, using existing tree traversing algorithms and the algorithm provided by the authors of this research paper have done using these ablation studies. So the result is better when we use the mapping function. If you see here, if you see this results, this
I
two,
see.
yeah, for that purpose they use that one.
Okay, thank you. Yeah.
이게 제 생각으로 이제 프리오더를 이용한 거는 프로그램의 이제 그 스트럭처를 제일 잘 반영할 수 있어서 프리오더나 인오더나 이제 포스트 오더 중에서 이제 프리오더를 이용한 것 같은데요. 그러니까 프로그램을 위에서부터 이제 순차적으로 이제 시퀀스 단위로 이제 우리가 이제 읽는다고 했을 때 프리오더 트래버스를 해야 그 구조를 이제 제일 잘 반영을 하는 매핑인 것 같아요. 근데 이제 프리오더가 DFS의 일종인데, 걔네 프리오더가 DFS의 variant잖아요. 여기서 depth first search잖아요. Pre-order search is a kind of depth first search. 근데 여기서 사용한 depth first search는 어떤 depth first search를 얘기하는 거예요?
그건 지금 저도 잘 확인 못했습니다.
그러니까 depth first search라고 하면 이제 브랜치, 그러니까 뭐 계속 리커시브하게 이제 리프로 가는 거긴 한데, 같은 차일드가 이제 여러 개 있을 때 어떤 걸 선택할 건지에 따라서 좀 달라질 수 있을 것 같은데, 어쨌든 프리오더 설치를 하면은 그 depth first search여서 좀 부분이 좀 잘 이해가 안 됐고, 그다음에 그 프로그램의 구조를 반영하기 위해서 abstract syntax tree를 이용해야 된다라는 이제 좀 그런 인사이트를 이용하는 논문들이 많이 있는데, 이 논문의 이제 스터디를 보면은 abstract syntax tree를 이용했을 때 코드 서머리제이션이랑 코드 제너레이션에서 성능이 안 좋아지거든요.
네.
다른 태스크에 대해서는 성능이 높아지는데 코드 서머리제이션이랑 제너레이션에서 AST를 쓸 필요가 없는 것처럼 보여서
어, 그런데 코드 제너레이션이나 코드 서머라이제이션에서도 코드 T5 베이스 밖에 다른 기준 모델들은 유닉스 코더 보다 좋아지지 않을 것 같다.
그러니까 일단 코드 서머리제이션이나 제너레이션에서 코드 T5가 이제 어쨌든 유닉스 코더보다 좋은 것 같은데 앱스트랙트 신텍스 트리를 사용하는 게 정보가 더 많아서 그런지 서머리랑 제너레이션에는 더 이제 안 좋네요. 네. 코드 리페어나 이런 데에서는 AST나 이제 컨텍스트 플로 그래프나 뭐 이런 거를 고려하면 좋을 것 같긴 한데 어쨌든 네. 그거에 대한 더 깊은 분석은 없죠. AST를 썼을 때 그냥 안 좋다라고만 얘기를 하고 왜 안 좋은지에 대한 커멘트는 없죠.
음, uh, first, they have provide the they recommend that just they have provide some discrepancies on the retraining stage and the fine-tuning stage. They have also provided some solution for that, but still AST, the solutions without AST is better than the solutions with AST. But in all over the results, out of code T5 base, they do have some comparable good results with respect to other models other than code T5 base. I think this will be something future work.
그 테이블 2 관련해서 질문 있는데요. 뭐 비슷한
예.
질문일 수도 있는데 그러니까 AST, BFS, DFS 저거는 코드가 입력으로 들어갈 때만 대상되는 거 아닌가요? 근데 코드 제너레이션은 NLP가 그러니까 내추럴 랭귀지가 입력으로 들어가서 코드가 나오는 건데 그러면은 아무런 의미가 없는 거죠, 지금.
아니 학습할 때 저거를 했다라는 프리트레인드 모델을 학습할 때.
프리트레이닝 할 때, 그럼 실제로
네,
저
프리트레이닝, 예.
제너레이션 태스크 할 때는 전혀 저걸 쓰지 않지만 이제
네,
트레이닝 할 때
네.
효과가 있었는가? 알겠습니다.
결국에는 이제 AST를 써서 그 모델이 코드의 시멘틱스를 더 잘 이해하게 이제 했다라는 게 이제 이 논문에서 제안하는 컨트리뷰션인 것 같은데 사실은 코드의 시멘틱스를 잘 이해했다라고 하면은 서머리는 잘 돼야 될 것 같거든요. 근데 이제 서머리도 비슷하긴 하지만 어쨌든 이시나 마나한 것 같고 제너레이션은 시멘틱스를 잘 이해하면 좋을 것 같긴 한데 뭐 크리티컬 하지는 않을 것 같아서 일단 코드 서머리는 좀 의외여서 네. AST가 별로 필요 없이 그냥 키워드 위주로 이제 서머리를 한다라는 것 같긴 한데요.
네, 그런 것 같습니다. 혹시 이 논문에 그럼 유닉스 코더는 지금 딱 트랜스포머 하나만 갖고 있는 거죠? 제가 알기로 PL바트나 코드 T5는 그 인코더, 디코더, 트랜스포머가 다 있는 걸로 알고 있는데 얘는 그냥 트랜스포머 하나를 그냥 인코더, 디코더, 뭐 인디코더 다 한꺼번에 학습시키는 거죠, 지금? 그 트레이닝
네,
objective만 다르게 해가지고.
네, objective에 따라 다 가지고 음역할 때는 segment embedding으로 어떤 objective로 트레이닝하고 있는지는 semantic segment embedding으로 파악할 수 있다는 알게 있습니다.
알겠습니다. 그러니까 유닉스 코더가 지금 레이어 수나 이런 게 만약에 PL바트랑 코드 T5랑 똑같다고 하면은 파라미터 수는 더 적겠네요. 그러면 오히려.
But the difference from the other models is I have referred the natural language version of this model because they have created on top of that model. They use actual same architecture. So they use segment embedding to determine whether the model is operating in decoder mode or encoder mode or encoder decoder mode. They use the same model, but they switch between these three modes, whether in encoder mode or decoder mode or
트레이닝 할 때
encoder
그렇게 하는
decoder.
거죠?
Yeah, yes.
오케이. So is this model available in the GitHub?
No,
No? Okay.
model only downstream tasks are released freely. The actual architectural design of the model is not available.
오케이. 혹시 질문이 있으시면 예, 저희가 아이디어라고 생각하는 1시간에 딱 2분 정도 남았는데 질문 있으신가요? 예, 너무 발표를 잘 하셔가지고 그런 것 같은데요. 예. 그럼 질문 없으시면은 오늘은 예, 여기서 그럼 마무리 하는 게 좋을 것 같습니다. 네. 오늘 좋은 발표 준비해 주신 계래 학생 정말 감사드립니다. 고생 많으셨습니다.
네,
감사합니다.
수고하셨습니다.
고맙습니다.